to Gifted and Science and Technology Physics class. I'm NC Joshua. Today we'll be looking at latent heat and specific latent heat. Now, the word latent means hidden, and it is a form that, or a form of heat that is not noticed, but it occurs, but it's not noticed. Now, what is latent heat? We said this is the quantity of heat required or given out to change the state of a substance. Take note, to change the state of a substance, to change the state of a substance at constant temperature. Take note of this. So the change occurs at a constant temperature. So it's as though that there is no change in temperature, but there is a change in the state of the substance. So that's why this heat that brings about this change in the state of the substance is now called latent heat. Now let me show you something in this graph. Now if you look at this graph here, you see that the substance is at minus 5 degrees Celsius. So, and at minus 5, the substance is existing as a solid. Let's take, for instance, water. We are using water as a case study. So, at minus 5, water will be a solid. At minus 5, water is a solid. Now, at minus 5, check what has happened. It has changed to 0. So minus 5 to 0 degrees. Now look at this. There is a significant change in the temperature from here to here. Now, when there is a change in the temperature, it is noticed. But look at this point. Now, what are we trying to say? At this point here, the substance is still solid. At this point, the substance is solid. So at 0 degrees Celsius, this same substance is still solid. But what happens? It undergoes a process to this point. So let's give this point here A, let's give here A, and let's give here B. So now between A and B, the substance has undergone a process. And what's that process? It's called melting. So the substance, which is water in the form of solid, which is ice, melts to this stage. Now, at this point, it is now in a liquid state. Now, watch this. At this point, it was ice. Ice changed to this point, still ice, but there was a change in temperature. I reiterate again, ice changed to this point, still ice, but there is a change in temperature. Now, A to B, there is now a change in the state. Look at it, solid, but now liquid, but still at 0 degrees Celsius. So A was solid, B now is liquid, but at the same 0 degree. So melting has occurred. The substance has changed from solid to liquid, but there is no change in temperature at constant temperature. That's what the definition is telling us. That is the heat required or given out for to change the state of a substance at constant temperature. Now look at another case again. This is liquid at B. Now, if you come to this point now, which is, let's give this point C. At C, this point is at C. Now, what is happening? This is still liquid at C. It's still liquid at C. Now, this is at 100 degrees Celsius. Remember, water boils at 100 degrees Celsius. So, at 100 degrees Celsius, something is happening. Remember, liquid here, significant change in temperature, but the state is still liquid. But as the water continues to boil at 100 degrees Celsius, something starts happening. So at this point now, which is my D, the substance is no longer in a liquid state. Now it's now in a gaseous state. So it means here to here, there is a change in the state of the substance, but there is no change in the temperature. The temperature is constant. So liquid is becoming gas. There is a change in the state. Solid is becoming liquid. There is a change in the state, but at constant temperature. So now we are not saying that there is an acquiring of heat, because for a solid to become liquid, it has to acquire heat to break the bonds that is binding the molecules together. So that heat that is acquired is unnoticed heat or to bring about a change in temperature. But this one that is acquired here is not bringing out or is not showing forth a change in temperature. Is unnoticed. It is hidden. We call such a heat latent heat. So there is latent heat from A to B and there is latent heat from C to D. There is no latent heat from -5 to 0. No. What is happening here is heat capacity. Specific heat capacity is happening here. What is happening here is specific heat capacity, a heat that is required to change the temperature of the substance. So this is the heat required to change the temperature of the substance. This is the heat required to change the temperature of the substance. So there is a change in temperature, 0 to 100, -5 to 0. So what occurs here is different from what occurs here. Here is latent heat of fusion. That's melting. Melting is fusion. You see it here. We have specific latent heat of fusion, and here you have latent heat of vaporization. Now, what is the difference between just latent heat and specific heat, specific latent heat? We'll say once it involves a unit mass of the substance, it becomes specific. So the difference between this and this is that there is not an addition of a unit mass. So look at it. The quantity of heat required to change the quantity of heat, the quantity of heat required to change a unit mass, which is 1 Kelvin of the substance. So this heat is either acquired or it is given out. So the quantity of heat either given out or required to change the state, to change a unit mass of the substance is what we call specific latent heat. I reiterate, the quantity of heat required to change a unit mass, which is 1 kg of the substance, is what we call specific latent heat. Now remember, this latent heat can be in the place of melting, solid to liquid. It can be in the place of vaporization, which is liquid to gas. So I can show you this graph here again in this manner. Look at the way I will show you the graph here now. Now, at this point, which is my -5 degrees Celsius, I have this. So what will be happening here is NC, change in temperature. There is a change in temperature. Why? Because this is -5 to 0. Now, what about this? I have here to here, there is no change in temperature. So since there is no change in temperature, I'll be having NL F, which is latent heat of fusion. Now, if I go from here to 100, now remember, here is 100. Now, if I go from here to 100, what is happening? This is 0 to 100 degrees Celsius. There is a change in temperature. So this is the MC change in theta. But if I go here, there is no change in temperature. So this is T, what again now? MLV. What is V? Latent heat of vaporization. Now, if it goes higher again, more than this, I will have MC change in theta. So anywhere I have a change in temperature, I have MC change in theta. Anywhere there is no change in temperature, I have the latent heat of that state. Meaning, if it's changing from solid to liquid, I'll call it latent heat of fusion. If it's changing from liquid to gas, I'll call it latent heat of vaporization. So the total heat required to change a state, to change a substance, which is at -5 degrees Celsius to 100 degrees Celsius. Now, look at it now. The quantity of heat required to change the state of a substance from -5 degrees Celsius to 100 degrees Celsius will now be given as, look at the quantity of heat. The first one is here to here, which is MC change in theta, plus here to here, which is MLF, latent heat of fusion, then here to here again, which is plus MC change in theta. Then this is the last point because I said at 100 degrees Celsius. Now it's not depending on is it at liquid state or at gaseous state. If it's at liquid state, I will stop here. But if it's at gaseous state, I will end here. So I will say come to R plus MLG. That's if it's at its gaseous state. So this will now be the total heat required to change a substance from minus 5 degrees Celsius to 100 degrees Celsius. Thank you. Now let's look at an example as regards heating heat. Now it says calculate the quantity of heat required to convert 500 grams of ice at, look at the temperature, this is a temperature for ice, at minus 4 degrees Celsius to water at 80 degrees Celsius. We are looking for the quantity of heat required for this conversion. Now look at this graph. Let's assume this graph. Now let's assume the graph that we are starting from minus 4 degrees Celsius. So what will happen? The substance, the ice, will go from minus 4 to 0. Minus 4 to 0, remember? Then from 0, it will melt. So it will melt still at 0. Then what's the next thing that will happen? It will go to 80. So let's assume that this point is 80. Now trace it here. This is 80 degrees Celsius. So you see that the curve is going to be in this manner from minus 4 to 0. What do we say occurs here? Since there is a change in temperature, what we have here is MC change in theta. Then from here, remember this place is still ice, but at this point is now liquid. As this point is still ice, but at this point is now liquid. Now, what happens from here to here? Melting. And if it's melting, what do I have here? I have NL. F, which is latent heat of fusion. Now, what is happening from here to 80? There is a change in temperature from 0 to 80. So, what I have here is MC change in theta. That's what I have here. So, my total heat needed is equal to MC change in theta plus NLF, latent heat of fusion, plus MC change in theta. Now, what about this MC change in theta? Now, what about this? This is for eyes. So everything occurring here is for eyes. What about this latent heat of fusion? Is still for eyes. So this is also for eyes. But what about this specific heat? This heat is for liquid. That's for water. So you take note of this, that this is for water, this is for ice, and this is for ice. Why? Because this is the point where we got this. So it's for ice. Why the heat here is NC changing theta. Here is latent heat of fusion, still for ice, but here is the heat for water, which is now MC changing theta of water. So how will I solve this now? So H will now be equal to, what is the mass given? The mass given is 500 grams, which will now be 0.5. So that will be 0.5 times, what is the specific heat capacity of ice? The specific heat capacity of ice is this, 2090. So 2090 plus, what is the change in temperature for ice? It's changing from minus 4 to 0. So it will be, look at this very well, it will be 0 minus minus 4. 0 minus minus 4. That's how I will express it. 0 minus minus 4. So that will now be plus. We are now adding that of this. Now, what is still the mass of the ice is still 0.5. 0.5 times, what is the latent heat of fusion? The latent heat, specific latent heat of fusion is 3.36 times 10 raised to power 5 times 3.36 times 10 raised to power 5. Then after that, plus, what is now the last case, which is this case? The last case is now the same mass, because take note, the mass of the ice is also equal to the mass of the water. Matter can be created nor destroyed. Matter cannot be created nor destroyed, but can change from one form to another. So the mass of the ice is equal to the mass of the water. So now I still have it as 0.5 times, what about its specific heat capacity of water? It was giving us here as 4200 times 4200, then times, what's the temperature change? It's changing from 0 to 80. So it will now be times 80 minus 0. So if you see now, I have brought out all the parameters from this equation or from this formula that I need to solve. I reiterate again, M for ice is 500 grams, which is 0.5 times specific heat capacity of ice, which is this, plus, sorry, times, not plus, times, what is the temperature change? It's changing from -4 to 0, so it becomes 0 minus 4. Why minus 4? It ought to be 0 minus 4. But remember, here is a minus, it's a negative sign. So 0 minus 4, close the bracket, plus, what is the mass of the ice? Is T 0.5? 0.5 times specific latent heat of fusion. Specific latent heat of fusion is 3.36 times 10 raised to power 5. No temperature change, remember, no temperature change. Now, plus, what is the mass of the liquid? The mass of the liquid is the same thing as the mass of the ice. When an ice melts, the mass of the ice is equal to the mass of the liquid. So it's now 0.5 times. What about this small letter C? Is the specific heat capacity of water times change in temperature. What's the change in temperature? From 0 to 80. So it's now 80 minus 0. So I hope you understood how all of these are for proper work now calculation. So now we'll now be having H will be equal to 4180 plus, that's everything here is this, plus everything here will be 168,000 plus everything here is the same, 168,000. So take note of this side is out. So what is now H equal to? H is now equal to 340,180 joules. So the heat required to convert ice from -4 to 80 degrees Celsius is equal to 340,180 joules. Now, how do you get it? We'll first of all show the way it will go, and these are the pathway. Then we said this is for ice, while this is for water. We'll look at another example to portray more
Now let's look at
points.
question number two. Question number two says 0.4 kg of water at 20 degrees Celsius is completely converted to ice at 0 degrees Celsius by extracting 168,000 joules of heat from it. If the specific capacity of water is 4,200 joules per kilogram per Kelvin, calculate the specific latent heat of fusion of ice. Now, if I take the table of this, I have at 20 degrees Celsius, I have water there. Water at 20 degrees Celsius is completely converted to ice. So if water loses heat, it will go down to 0. It will go down. This is water, H2O as liquid. But at this point, it is still H2O as liquid. So it has not been done. It has not been changed to ice. But remember, this is 0 degrees. So what will happen? It has to freeze. So this is freezing to ice. So this is freezing. So this is now ice. At this point, I have H2O but solid. So water from 20 degrees Celsius becoming ice will follow this pathway. Hence, here we have NC change in theta. That's the heat here. While here, the heat we have here is NLF, latent heat of fusion. But here there is a change in temperature, while here there is no change in temperature. So this process is not giving out heat. This process is absorbing. Sorry, this process is giving out heat. This process is not absorbing heat. That's what the question says by extracting. So it's giving out heat for the temperature to fall. You give out heat for freezing to occur, but you absorb heat for melting to occur and for boiling to occur. So now, what is our total heat? Our total heat is now equal to here to here first, which is NC change in theta plus here to here, which is now NLF. Now, what is the heat extracted? The heat extracted is 168,000. So 168,000 is equal to what is the mass? This is mass of water. Why is it that of ice? So mass of water is 0.4 times specific heat capacity of water 4200 times the change in temperature for water is changing from 20 to 0. So the difference is 20 times 20, then plus the mass is the same mass of water that is becoming ice. So I'll still maintain by 0.4. So it's 0.4 times LF, latent heat of fusion. That's what we are looking for, specific latent heat of fusion of ice. So now I have 168,000 is equal to, if you multiply everything here, you have 33,600. 33,600 plus 0.4 LF. Now take this way, I have 168 this times, and I have minus 33600 is equal to 0.4 LF. So I have 134,400 is equal to 0.4 LF. So what is now our LF equal to? Is equal to 134,400 over 0.4. That will now give us LF to be equal to 336,000 joules per gram per kilogram. So that becomes the final answer to this question. Thank you.
Now let's look at another example, example 3. It says 60 grams of ice at minus 5 degrees Celsius is placed in 100 grams of water at 80 degrees Celsius. Now you take a note of this. Ice is at 5 minus 5, water is at 80 degrees Celsius. If the final temperature after all the ice has melted is 19 degrees Celsius, meaning that the ice has gained heat to melt. So if I have a graph like this, please look at this graph very well, very important. This is minus 5, this is 0, and this is 80, where that's the highest temperature we have in the question. This is 80, this is the degree Celsius side. Now look at this again. Now if the ice is here, for ice to move from minus 5 to the final temperature, our final temperature is 19. Remember, it will gain heat. We discussed this already in heat capacity and specific capacity. We said that the heat loss by the water is equal to the heat gain by the ice. So here we are having ice Moving from minus 5, first it will go minus 5 to 0. Then from 0, now remember it's ice here. At this point it's still ice, but it will now melt. At this point it's now water. Remember this, then it will now go to 19. So let's take this point to be 19. This is 19. This is the temperature of the mixture. This is 19. So this is where it stopped. Now remember, there is another person coming from here, which is 80. Now, which is that? That is water. 100 grams of water at 80. So it means that this will come down straight to meet this. So what is happening here is that it's losing heat. So from here to 19, is just MC change in theta. But from here to 19, from here to 19 is TMC change in theta. From here to here, there's a change in temperature. Anytime there is a change in temperature, it is MC change in theta. So here to here is TMC change in theta. But here to here is now MLF, latent heat of fusion. Take note of this because once you know these graphs, it's more easier to understand the question. I repeat again, we have water here at 80 degrees Celsius. We have ice here at minus 5 degrees Celsius. What happened? We were told that ice was not added to water, or water, yes, ice is placed in water. Ice was added to water. When ice is added to water, what happens to the ice? It will absorb heat from the water and it will melt. So we are not saying that ice at minus 5 degrees Celsius, this is the process at which it will melt. So what temperature did both of them now agree to be in equilibrium? It's 19 degrees Celsius. So ice melted to 19 degrees Celsius, which is now water. Then the water that was at 80 degrees Celsius, the temperature will drop, but the temperature of ice rose to 19, while the temperature of water fell to 19. So it means water lost heat, but ice gained heat. So the heat that ice gained, how is the pathway? It was from minus 5 to 0, which is MC change in theta. Then from minus 0 to still minus 0, that is the melting. Because at this stage, it's still ice, so it has to melt. That's why we now have MLF. Remember, there is no change in theta when there is a change in the state of the material or in the state of the substance. Why? Because the heat change is not observable. That's why we call it hidden heat. So from here to here is 0 to 0, but the state is changing. Ice to water, liquid. So we now said it's now this to this plus this to this, which is now MC change theta plus NLF plus this place now to this place. This is liquid, this is liquid. But 0 to 19, there is a change in temperature. It's now MC change in theta. So what would I say now? I would say heat loss by water is equal to heat gain heat gain by ice. Now let's look at how this can be rectified. Heat loss by water is just from here to here, from 80 to final temperature, which is 19. So it will just be MC change in theta of water is equal to, what is the heat gain by ice? This is ice from here gaining heat to 19. So all of this pathway till 19 is what is the heat gain. And what is it? From here to here is MC change in theta, which is MC change in theta of what now? Of ice plus, what's the next one? Ice to water, latent heat, no change in temperature. So this is the specific latent heat of fusion, which is plus NLF, then plus From here now, which is now water, to 19 is MC change in theta of what now? Of water. This one is of ice. So this is the expression that will help us calculate for the unknown in this question. Now, what is the mass of water? Mind you, 60 grams of ice. So the mass of water is not 60. Is placed at minus 5 degrees Celsius, is placed in 100 grams of water. So the mass of water is 100 grams. So now let's see that to be, this will now become, what is this? 0.1 kg, that's 100 grams, times, what is the specific heat capacity of water? 4,200 times, what's the temperature change for water? It's changing from 80 to 19. So that will be 80 minus 19 is equal to, what is that of ice? The mass of ice, this is no longer 100 because this is now ice. The mass of ice is 60. So that would be 0.06 kg times, what is the specific heat capacity of ice? Specific heat capacity of ice was given us in our question is 2,100. That's 2100. Then what's the next thing? The change in temperature for ice is minus 5 to 0. So the difference is 5 times 5 plus, what are we adding to it? We are not adding this. In adding this, the mass of ice is still 0.06, which is now 0.06 kg times, what is the specific latent heat of ice? We were not given that in our question. That's LF. Then we have again plus, what are we adding now? We are not adding this, which is this side. We are adding this. Now, question, is this M mass of ice or water? It's mass of water. Which water? The ice has now become water. So the mass here is the same thing as the mass here. But the mass here is not the same thing as the mass here. This is 0.06. That's from your 60 kg of ice. The same mass is here and the same mass is here. So this mass here is actually 60 grams, not 100 grams of water. So now I'll be using here, which is this, as 0.06 times specific heat capacity of water is 4,200 times, what's the temperature change? 0 to 19. So the difference is just 19. This is the expression. Now, what will now be my equation further? I will now have, for everything here, I will have 25,620. 25,620 is everything here, is equal to, what is everything here? I will have it as 630 plus, what's the next one? It becomes 0.06 L plus, what's our last figure? We have 4788. So if you take this out, you now have it as 25620 minus open bracket 630 plus 4788 is equal to 0.06 L. What do we have here? We'll now be having 220,202 is equal to 0.06 L. Therefore, what is now L? L, which is now your latent heat of fusion, is equal to 2202 divided by 0.06. What becomes the answer? It becomes 336,700. So latent heat of fusion is joules per kilogram. That becomes the final answer to this question. Now let's look at another example to strengthen our calculation ability. How many grams of water at 17 degrees Celsius must be added to 42 grams of ice at 0 degrees Celsius to melt it completely? Now look at it again. If we are using the same graphical method, we have ice. How many grams of water at 17? So at 17 degrees Celsius, we have water. So here is H2O as liquid. Now we are saying how many grams of water must be added to 17 how many grams of water at 17 degrees Celsius must be added to 42 grams of ice at zero. So at ice, remember ice at zero. This is ice at zero. This is also water at zero. This is ice at zero. This is water at zero. Remember, this is liquid. This is ice. So if ice becomes liquid, there is no change in temperature. It's still at 0 degrees. There is no change in temperature, but there is a change in state because ice is H2O solid. So solid is becoming liquid. So from here to here, what happens is MLF, latent heat of fusion. But from here to here, what happens is what MC, change in theta, because there's a change in temperature from 0 to 17. So what is the concept? Heat loss equals heat gain. Which one is losing heat? The ice is losing heat while the ice is gaining heat. So I will say heat loss by water equals heat gain by ice. So what is heat loss by water? It's just here to here. So now the question now, remember we said the question says how many grams of water at 17 must be added to 42 grams of ice at zero to melt the ice completely. So to melt the ice completely is to be at this stage. So to melt ice completely is to be here. So water is coming down here, ice is coming to this point. So I have heat loss by water, which is now MC change in theta is equals heat gain by ice is just MLF. Now this is for the water, while this is for ice. So what is the mass of water? We don't know the mass of water. That's the question. How many grams of water? So I have mass of water times specific heat capacity of water is 4,200 times what's the change in temperature? 17 to 0. So that is 17 is equal to mass of ice is 42 grams. So 42 will now be 0.042 times, now that's in kg, times what's the specific latent heat of fusion of ice? We have it as 3.4 times 10 raised to power 5, not minus 5. 3.4 times 10 raised to power 5. So it becomes 3.4 times 10 raised to power 5. So what is now the mass of water? Mass of water will now be 0.4 0.042042 times 3.4 times 10 raised to power 5 all over, I have it as 4200, then times 17. Now this can be very easy for us. 1, 2, 3 cancels here, you have it as 2. Then this takes up this, you have this as 100. Then 2 here takes up this. Then I now have this as just, I have this as 3.4 over 17. That will be 0.2 kg. 0.2 kg can also be 200 grams. That becomes the answer to this question. Now let's look at example number 4. Sorry, example number 5. It says dry steam at 100 degrees Celsius is bubbled into 300 grams of water initially at 25 degrees Celsius. What will be the temperature of the water after 20 grams of steam has condensed? Now it means that if I have it as a graph like this, if I have this as a graph, now please take note of this, very important. At 100 degrees Celsius, at 100 degrees Celsius, water boils. So if I have this at this stage, now remember, then if this is water, if this is water, H2O, if this is H2O as liquid, then as it goes here, it's still H2O, but now as gas. So this is actually water changing to gas. That's steam. So what about this? We said dry steam at 100. So this is steam at 100. This is water at 100. What is condensation? Look at the word here. Condensation is when gases becomes liquid. That's condensation. So now this gas will come towards the liquid side is what this question is telling us. So dry steam at 100 degrees Celsius is bubbled into 300 grams of water. So how would this case look like? The steam will lose heat while the water will gain heat. So heat lost by steam is equal to heat gained by water. So now dry steam at 100 degrees Celsius is bubbled into 300 grams of water initially at 25 degrees Celsius. So let's see 25 degrees Celsius. At 25, we have water. Let's see that we have water at 25. So this is water at 25, H2O as liquid at 25. So now let's see that we have what will be the temperature of the water after 20 grams of steam has condensed. So when we put steam into water, this temperature of the water that is at 25 will definitely rise, while the temperature of the steam will definitely fall. So heat gain by water is equal to heat loss by ice. So now what is now the heat loss? Now remember, we're not looking for the temperature at which it will be. What is condensation? Condensation is gas becoming liquid. So from here to here is actually NLV. From here to here is latent heat of fusion. Sorry, latent heat of vaporization. What about from here to here? From here to here is actually MC change in theta. But mind you, that there's going to be a meeting point within this region because this thing will cool to come to this point, a point here, while the water will rise to meet that same point. So condensation will occur from here to this point, then it will go down again. So I have this coming from here to here, having MC change in theta, while this also rising as MC change in theta. There is a meeting point somewhere, but I cannot tell where that meeting point is. So it's that temperature of that meeting point that we are looking for. I explain again that when you bubble steam into water, the steam will lose temperature while the water will gain temperature. The heat loss of the steam is equal to the heat gain of the water. Now, we were not told that what would be the temperature of the water after 20 grams of steam has condensed. What is condensation? Steam changing to water. Now, remember, all through this point is steam changing to water. Sorry, is water changing to steam. Now, steam is now coming back to water. So as it's coming back to water, we want to know what is the temperature, at what temperature will this steam now finally become water when you have 20 grams of steam being condensed. So now I say heat loss by steam equals heat gain by water. What is the heat loss by steam? It will be from here to here, which is now NLV plus What about here? I have NC change in theta is equal to heat gain, which is just NC change in theta. Now, remember the temperature we're looking for, we'll see it soon. What is now this? The mass of steam that was given us in the question is how many? Is the mass of steam, dry steam, and this is bubble into. So the mass of steam is 20, is here. So we have 20. 20 will now be 0.02 times specific latent heat of vaporization. As this specific latent heat of steam is 2.26 times 10 raised to 6 plus what is the mass of steam? So this becomes plus the mass of steam. Now remember, this is now water. This is for steam, while this also is for water. Look at it for steam. This is now steam becoming water also. So now this plus this times this plus mass of the steam that is now water is the same thing as 0.02 times specific heat capacity of water, which is 4200 times temperature change. Now, at this point to this point, we do not know the temperature change, but what we know is that it is 100 minus theta. So it becomes 100 minus theta is equal to, now I've done everything here, is equal to, what is the mass of water? Mass of water is 300, which is 0.3 times specific capacity of water is 4200 times, what's the temperature change? Is changing from this particular 25 to that unknown temperature, which is somewhere around there. So it becomes theta minus 25. So is theta I'm looking for in the question. So this is 45,200 plus this becomes 84 bracket 100 minus theta is equal to, so this becomes 1260 open bracket theta minus 25. So what becomes our next? We now have 45 45,200 plus 8400 minus 84 theta is equal to 1260 theta minus 31,500. So what do we have here now? Colored light terms, we now have 45200 plus 8400 plus 31500 is equal to 1260 theta plus 84 theta. So this becomes 85,100 is equal to 1344 theta. What becomes theta is now 85,100 over 1344. So theta is, we'll be having theta equals 60.64 degrees Celsius. So it means that the theta here, that the temperature of the water will rise to on steam condensing to water is now equal to 60.64. So that is the concept of this: heat loss by steam equals heat gain by the water.